Hello, my name is Mike Heap, and I'm from the University of Strasbourg in France. And today I'll talk about the permeability of granite deformed in the brittle regime and the implications of these data to the permeability of fractured geothermal reservoirs. The work I'll present today is part of a larger project called Geothermal, which aims to explore the geothermal potential of crustal fault zones. So in these systems, hot fluids are transported from close to the brittle ductile transition to the surface through crustal scale fault zones. The case study that we're focusing on in the project Geothermal is the Pont-Gibaud area in the French Massif Central. And so in the context of the Geothermal project, we performed triaxial deformation experiments on samples of granite to large strains in the laboratory in order to look at the influence of brittle deformation on the permeability of granite at different effective pressures corresponding to different depths. And so the work I'll present today is the preliminary findings of this laboratory investigation. A brief note on the materials and methods. The granite used in these experiments was Langelaan granite from France. Here is a optical microscope image of the granite. And this granite was thermally cracked prior to the experiments so that we could measure the permeability of the sample over reasonable experimental timescales. The connected porosity of the granite after the thermal cracking is about 1 to 2%, and this comprises almost entirely of microcracks. So the samples were vacuum saturated in water and placed inside a triaxial deformation apparatus. So this is the schematic on the right, where the sample is located in the middle here. And then triaxial deformation experiments were performed at a constant strain rate in which the permeability of the samples was measured intermittently during the deformation. So in total, 3 deformation experiments were performed at different effective pressures of 10, 30, and 50 megapascal. So these are the mechanical data. What we can see on the top here are differential stress as a function of axial strain for the 3 experiments. So these are stress strain curves. And let's look at one of these in particular. So what we have is an initial loading, eventually to a peak stress, followed by a stress drop, which is the formation of a macroscopic shear fracture. And after the stress drop, we have sliding on the formed fracture up to axial strains of almost 10%. So on the bottom here, we have the porosity change as a function of axial strain for these same experiments. And so what we can see for all 3 experiments is that there was initial reduction in porosity associated with the closure of microcracks as the sample is being loaded initially, followed by an increase in the porosity as the shear fracture forms. And then as the deformation is accommodated by sliding on the fracture, we see a steady increase in the porosity. So if we look for differences between the mechanical behavior of the 3 experiments, we can see first that the peak stress required for the macroscopic failure of the sample increased as a function of increasing effective pressure. So at an effective pressure of 10 megapascal, the peak stress was just more than 200 megapascal, and an effective pressure of 50 megapascal, the peak stress was about 500 megapascal. We also see differences in the evolution of porosity change in that the increase in porosity as a function of axial strain is higher for lower effective pressures. So at the end of all 3 experiments, the samples, when they were retrieved from the machine and from the jacket, contained a macroscopic shear fracture like the one in the picture shown on the right-hand side here. So here's an example of the permeability data, which were collected using the steady state method during deformation, in which we stopped the loading of the sample. We measured the permeability using the steady state method, and then after we continued the deformation of the sample. So this is an example of the data for the experiment performed at 10 megapascals. So what we can see is the stress strain curve that I described earlier. And these points here are the permeability data. So what we can see is that as the sample loads up to the peak stress, we see that the permeability decreases by approximately an order of magnitude here. So it decreases from a permeability of 10 to the minus 16 down to a permeability of about 10 to the minus 17. Upon the formation of the macroscopic shear fracture, which is also shown in this small inset here, we see that there's an increase in the permeability of the sample. And then as the deformation, as the strain is accommodated by frictional sliding on the macroscopic shear fracture, we see that there is more or less no change in the permeability of the sample up to the maximum strain of about 10%. So here are the permeability data, or the permeability evolution as a function of axial strain, for all three of the experiments that were performed for this study. So to remind you, we performed an experiment at 10 megapascal of effective pressure, 30 megapascal and 50 megapascal. So this is very similar to an increase in the target depth. So the experiment that we discussed before was the experiment performed at 10 megapascal, and we discussed how the permeability decreases as the sample is loaded up to the peak stress. And then after the formation of the macroscopic shear fracture, we see an increase in permeability. And then as the deformation is accommodated by sliding on the fracture surface, we see that more or less the permeability doesn't change up to a strain of about 10%. So what we can see from the other experiments is, as we increase the effective pressure, that qualitatively the evolution of permeability of the sample is very similar. We see decreases in permeability here and here as we are loading the sample to the peak stress. We see increases in permeability of the sample following the formation of the macroscopic shear fracture. And in both cases here at 30 MPa and at 50 MPa, we see that the permeability doesn't really change as the deformation is accommodated by frictional sliding. And so the evolution of permeability is, in the three experiments, is qualitatively very similar. Quantitatively, what we can see is that the final permeability of the sample is less as the effective pressure is increased. So at 10 MPa, the final permeability of the sample was approximately 10 to the minus 17, and at 50 MPa, the final permeability of the sample was approximately 10 to the minus 18. So these next graphs show a summary of the permeability data for the three experiments that we performed. So this top graph shows the permeability as a function of axial strain for the three experiments performed at an effective pressure of 10, 30, and 50 megapascal. And this bottom graph shows the permeability as a function of the porosity change for these three experiments. So these summary diagrams show what I've been describing in the previous slides, in that the permeability evolution for the three experiments is qualitatively very similar. We see a decrease an increase due to macroscopic shear fracture formation, followed by a more or less constant permeability during the frictional sliding on the fault surface. Qualitatively, they're very similar. Quantitatively, the permeability of the sample at the end of the experiment is higher when the affected pressure or depth is lower. So to present the conclusions so far, what we've done is we've deformed samples of granite in a triaxial press whilst measuring their permeability at different affected pressures. What we've seen from the experiments is that the permeability of the sample decreases prior to the peak stress, and this is due to the closure of pre-existing microcracks. We've also seen that upon the formation of a macroscopic shear fracture in the sample, that the sample permeability increases slightly. And finally, we've seen that sliding on the macroscopic fracture to very large strains does not appreciably change the permeability of the sample. And so quantitatively, the permeability evolution from the free samples was very similar. Quantitatively, we see that the permeability of the sample at the end of the experiment is higher at lower effective pressures or depths. So these are the conclusions so far from this experimental study. And the next steps is to try to integrate these data into large-scale fluid flow modeling to try to understand the influence of fractures and deformation on the permeability of large-scale rock masses and reservoirs. So thanks for your attention. And if you have any questions, then feel free to ask them in the discussion part of this conference. Thank you very much.